Ramanujan for G is now available on the Google Play Store. Try it out for free.
All right. So last time we looked at various aspects of um, the thermal properties of matter. We explained how there is this concept of latent heat, and then we also looked a little bit at the ideas around calorimetry, right? And in calorimetry, what we did was we looked at heat loss and heat gain, right? So, um, and then we said ms delta theta is the heat, and when when it changes state, it is m times l, right, where l is the latent heat. Now, so what exactly happens in these cases? There is one body which loses heat and the other body which gains heat, and the heat loss is equal to heat gain in a closed environment. Now, we looked at heat as a separate idea, right? When we looked at heat loss versus heat gain, right? Now, in thermodynamics, we don't look at heat as a heat alone. You know, we look at a system, and then we look at how there is a transformation from multiple forms of uh, on the one hand, heat, which is a form of energy, heat energy, right? And work is what is achieved often through heat energy, right? Today, um, the world over, you know, different types of fossil fuels are burned. Today is Earth Day, 22nd of April. Uh, Different types of fossil fuel are burned in order to convert. By burning a fossil fuel, what do you perform a chemical reaction which produces what is known as enthalpy. Which there is an enthalpy of a chemical reaction, right? Now that produces a form of heat, and that heat is then transformed, is then used to do work. Okay. Now, this form of use of heat to do work, right, was one of the great inventions of the 19th century. With the invention of the cotton gin, and more importantly, the invention um, um, of the engine, IC engine, internal combustion engine, right? We first had the emergence of the railway, you know, and and the railway created the ability for humans to transform the landscape and conquer large areas and continents, and transport both cargo, people, over long distances. And so the great railroads were built. In India also became a part of this when they made a rail between Bombay and Thane first, and then they built the Great Indian Railway. Right now, in the United States also, there was the linking of the West, the exploration of the West, which happened partly through the use of long railroads into the West. And so the railroads formed the basis of how the how the world was subdued and conquered, and commerce became a critical part of what happened. This later, the use of oil steamers emerged. Initially, a lot of oil was obtained from whales, and then they were killed and slaughtered in order for oil. Later, it was then transformed they dug the ground and then they pulled out oil, and that was also used to facilitate the commerce through ships, through large oil resources were used to power ships against the wind. Previously, the wind was the driver of the ship, right? You have all seen since the days of the Indus Valley, where ships were made, which used to go long distances in the seas, right? Uh, the first emergence of these powered ships with ships powered by icy engines happened very recently. And so now, so thermodynamics drove knowledge of thermodynamics drove and understanding of thermodynamics facilitated this. And thermodynamics was people like Cartwright, Kelvin, and others, who formed the various who brought order. Carnot, all these people, they explained the way these systems are to be studied. So now let's move on to, with that introduction, let's move on to the definition of a system. The system in so thermodynamics is actually a very precise science. Okay, although they may teach it in like a history or something like that, right? It is just like your mechanics. Okay, you must understand the concepts very well, and you will learn it multiple times. Okay, and the better you understand the concepts, the better you will be in those subjects that involve that significantly involve thermodynamics, whether it is chemical engineering, mechanical engineering, etc. Okay, so now a system is whatever we want to study, but the most important point, it could be an entire power plant, it could be a an air conditioner, it could be a fridge, refrigerator, right? It could be many different things. Now, it could be a pipeline, right? So, but most often in a system is something which is enclosed, which has a boundary. And there are things that are inside the boundary, and there are things that are outside the boundary, and nay shall the two interact by means of motion of matter. The matter contained within the walls of the tank are closed. A boundary is defined, a Lakshman Rekha, and you cannot cross, and the matter inside cannot go outside, matter outside cannot come inside. So that is the nature of the Lakshman Rekha in a system. Now, a closed system consists of both of a fixed amount of mass, and no mass can cross the boundary, but energy in the form of heat or work can cross a boundary. If even that is not possible, it is called a isolated system. So the volume of a closed system is not fixed. Okay, so you can transform the volume, and the impact on that is what decides it. Now, an open system, right, is what is called a control volume. Okay, so typically when people say system, they typically mean closed system. Okay, but an open system is what is called a control volume. In a control volume, air or something else can come and go. Okay, so it comes into the system, does some work or some action, goes through some change, and then it goes out. Now the so all these systems are studied from that point of view. So if you take, for instance, the most common idea in these system theories involving thermodynamics is the use of heat. Okay, they necessarily involve heat. The car that called the Tesla, right? The car Tesla does not have an IC engine. For in India also, there are these electric scooters, no IC engine. Okay, or there is the Mahindra. For some time they have also an auto now. The Mahindra auto, it was essentially only an electrical system, There is an electromechanical platform. These platforms, on the other hand, which involve thermodynamics, involve some form of a heat based engine, and that is where thermodynamics plays a crucial role. And this kind of systems where the norm, and they are the norm even today. The normal car which takes petroleum involves these kinds of thermodynamic systems, and these are very well understood, studied, and form a very big industry. Now, the system boundary should be carefully defined with respect to a thermodynamic analysis. These are very important ideas. So typically you have a control surface, control volume is defined. So you say that I'm now defining a area. Okay, now I'm going to study this area and the various things that happen here. There could be mass coming in and going out. Both mass and energy can change in a control volume. Okay, so that is a very important idea. Now, heat, for instance, can cross the electromechanical can cross the boundary, as can work can be done on the elements inside the control volume. Okay, so that's like a motor or a pump, right? What happens in a pump, right? In a pump, for it, let's say you have a water pump, right? A water pump pulls water out, right? So the water enters the pump and then it leaves the pump, right? So there is a you can define if you define the pump as a control volume, there is of course the water that comes in, the water that goes out. So that's why it's a kind of control volume. Now, selecting the system to boundary should be done carefully. The objective of analysis, proper choice of the system may greatly simplify your analysis. So now the there is two kinds of thermodynamics. Okay, there is the kind that deals with the micro side of thermodynamics known as statistical thermodynamics. Many of you would have heard of, for instance, Boltzmann, Stephen Boltzmann's law, right? Or Bose-Einstein statistics. These are all forms of statistics and statistical thermodynamics in the microscopic side. But there is also the macroscopic approach to thermodynamics, which is known as classical thermodynamics. This is where Kelvin and the others who made the laws of thermodynamics came into play. Okay, so there, so that is what we call as classical thermodynamics, as a range of engineering applications, and you switch on your lights, most likely um, the electrical energy that comes to the wire to your house comes from a thermal power plant. Only few power plants are nuclear or based on, say, generators which are from water, that is from hydroelectric power plants, right? Hydroelectric, there is no thermodynamics in a hydroelectric plant. Or you can say one can kind of argue that. Okay, but most other plants will involve the combustion of either coal or natural gas or some other fossil fuel. Okay, these are all the result of thermodynamics. So now a property of a system is a characteristic of a system. So pressure, you already looked at, learned some of these things. There's pressure and volume. These are all properties. Energy is a property. Mass is a property. Temperature is a property, right? Now, state refers to the condition of system as described by the definitive values of these properties. We say that a process happens when a system changes state from one value to another. So it has, let's say something has this bunch of property A and this bunch of property B, moves to another state too, whereas this bunch of property A and this bunch of property B. Now, when you have, and so when it goes from one place to another, it goes through a process path, right? Now, some processes are reversible, some processes are irreversible, some processes involve a change of state from one state to another, which cannot be reverted back. Okay? In some cases, the properties that you are studying may be reverted back, but not all the properties involved. Okay? Now, in some cases, the process is itself such that one or two of the properties are kept constant. Those are all iso-based processes. So if you say isobaric, pressure is kept constant, isochoric, volume is kept constant, etc. Right? Isothermal, temperature is kept constant. Right? So these are all important ideas that one must understand. Okay, so a property is called extensive. It is a value for an overall for the overall system, the sum of its values for the parts. For instance, mass, volume, and energy are extensive. Now, intensive properties are things like pressure and temperature, which are independent of size. Okay, extensive is summation, intensive is not summation. Okay, now some specific properties are extensive and intensive, right? So you take an extensive property and then you to, like, for instance, density is a mass per unit volume or volume per unit mass. Those kinds of properties can be specific properties, which are actually uh, you know forms of intensive property, right? So uh, you know um, pressure itself, you look at it, is newtons per meter square, right? So in some ways you can think of even pressure as a it is an intensive property, but it is a can be thought of as a specific property. Some specific properties are intensive, right? So thermodynamic equilibrium, right, is an equilibrium state. There are different types of thermodynamic equilibrium. Now, mechanical equilibrium is related to pressure, right? So if there is no change in pressure at any point in the system, things are always moving in a system, right? There's no balance, right? Now, but then if you are able to maintain a balance, then we say there is mechanical equilibrium. And then there is also thermal equilibrium if we say the temperature is same throughout the system, right? So let's say typically if you look at these engines, right, the engine driver of a coal-based railway engine, right, the engine driver is shoveling coal into the system to keep the fire burning at a certain rate. The speed of the engine keeps moving at a fixed rate, and then every now and then he will push some extra coal into it. If he kept putting more coal, then it can temperature can go up. There are ways to control that, right? Too much back, if the engine went faster and slower, faster and slower, faster and slower, everybody will waking up, and eventually they will curse the engine drive, right? So the and that is one plus of using modern diesel based engines. Most engines today in India run on diesel, right? But then you can run them on, you can have also new engines, different engines which use coal. Now, thermal equilibrium, if the temperature is same throughout the entire system involves no temperature, which is the driving force for heat flow. Okay? Chemical equilibrium, if its chemical composition does not change with time, that is, no resultant chemical reaction occurs. Things are at chemical equilibrium. You know this sign, right? That in chemistry is a sign of chemical equilibrium. Okay, so thermodynamic equilibrium, thermal equilibrium, this is temperature is constant, mechanical equilibrium, pressure is constant, right, etc. Now, so reversible processes or quasi-equilibrium processes, like where, let's say, the moment, now let us consider this as it undergoes a change in state. The moment the weight is removed from the piston, mechanical equilibrium does not exist. As a result, the piston is moved upward until mechanical equilibrium is restored, right? Quasi-equilibrium is one in which the deviation from thermodynamic equilibrium. So here what is happening, right? Here there is a weight which is pressure ring, right? The weight m times g, right, is spread out over the area of this system, and now when the pressure of the gas goes to times the area of that the piston, right, the area of the piston times the pressure of the gas equals the weight, then the weight is going to be stationary, right? N newtons per meter square is pressure, right? So mg equals P times A. When mg equals P times A, that weight is going to be steady. I remove some weight, the gas is going to expand, right? And then it's going to move up. So again, it will reach a stage where N equals, mg equals the new M times G equals new P times A, right? And therefore, we will have a maybe considered an equilibrium state. So that's how these things work. Okay? Quasi-equilibrium can be viewed as a sufficiently slow process that allows the system to adjust itself internally so that properties in one part of the system do not change any faster than those in other parts. For non-quasi equilibrium, you're not able to characterize the entire system. Some things are happening in one place, something are happening in another place. Maybe we are not able to exactly say if there is some uniformity. Now, if there is some uniformity, it's the deviation from thermodynamics is infinitesimal. Okay, so it stays in an equilibrium process. Things are at balance. Equilibrium means what? There is a balance between the things that are happening inside. Okay, so quasi equilibrium can be viewed as a slow process. So once the engine driver has built has created momentum for the wheels, then he is adding coal at a fixed amount of time into the system and driving the engines at a constant rate, and it's moving at a constant rate. So here you have a PV diagram of a compression process, right? So you have an initial state here, then you compress it. That's this point, initial state at this point. The pressure is lower, right? Now when you compress it, the pressure increases and the volume decreases. So you have a movement this way, right? So PV is a constant, right? So that's what they're trying to prove. So PV equals the constant is a parabola, Boyle's law, right? So now work is the energy associated transfer associated with a force. So let's say you applied a force, you do work, right? So typically in thermodynamic systems, work done by the system. So you take the engine, right? Work is done by the system. That is considered positive, right? So in a steam engine, right? Work is done by the system to run the engine and move the train, right? Mechanical work, right? Mechanical work only moves the train, right? Now, when work is done on the system, like here work is done on the system by the person who's pushing the pressure, then we say that work is negative because this is the system. You see the system is this dotted line inside. It is a closed system, right? So in this case, work is done on the system, therefore the work is negative. So no, remember this picture, minus W plus W. Okay, so PdV, integral PdV, we say P is constant isobaric, V is constant isochoric, PV equals constant, PV equals nRT, as you know it is isothermal, and polytropic is PV to the power of n is a constant. We say that's a polytropic process. Okay, so remember these four definitions. Bar always deals with mercury. Okay, bar is mercury, and we always talk about um, um, baric is typically pressure. Now choric is volume. Volume is a constant. What is constant? Only they tell. Iso is constant. Okay, isobaric, pressure is constant. Isochoric, volume is constant. Isothermal, PV is a constant because PV is equal to nRT. Therefore, note this equation. How do you end up with this, right? PdV is what? P is what? 1 over K over V. So when you have K over V dV, you integrate dV over V, you will end up with ln V. And then you have v2 minus v1, right? Ln v2 minus ln v1, right? Therefore, you have isothermal producing a resultant in terms of the work is, so integral p dv is the work. Okay. Now, in an isochoric process, there is no dv. So the work done is zero. In a isobaric process, p is a constant, so it just becomes integral dv, which is v2 minus v1. Okay, so understand this, how these are derived also, and how we end up with this. Okay, so this pv to the power of n equals constant polytropic process, you understand how this is done, right? Now here again you replace v with k over v to the power of n, right? So you have v to the power of minus n, so you have v to the power of minus n dv. Integral of that is v to the power of minus n plus 1 by n minus 1, 1 minus n. We have P2 V2 minus P1 V1 by 1 minus n. Okay. And so, understand how the integral is done in each of these cases. That's very, very important, because a lot of questions they will ask just to check if you understand isobaric, isochoric, etc. Okay. So you must know these ideas because they are very, very critical. Heat is similar. Only thing is, when you supply heat, it is considered positive. When you transfer heat to the system, it's positive. When you do work on the system, it is negative. So heat into the system is positive, work done to the system is negative. When the system does work for you, it is positive. Okay, so that is the natural convention in thermodynamics. I supply heat, I get work, like in the steam engine. Remember the steam engine? You supply heat, it does work. Steam engine is the natural positive story. Okay, now temperature. The property temperature is a special thing with respect to thermodynamics. You don't have temperature in other places, right? Temperature tells you how warm something is, right? And temperature is a key determinant. Okay? Now, in addition to temperature, there's also this term called entropy. Okay? These two are central to the study of thermodynamics. Okay? So now we make certain assumptions in addition to understanding temperature, right? We make certain assumptions from the kinetic theory of gases. Okay? We will study kinetic theory of gases also in very soon. Okay, but first, maybe we should have done that before we came to thermodynamics. But let us remember the kinetic theory of gas. So ideal gas theory is what? What is the ideal gas equation? PV equals nRT, right? Now the ideal gas equation is often replaced with what is called the real gas equation. The molecules in the kinetic theory of gases, which kind of derive PV equals nRT, assume that the gas obey Newton's law of motion. They have, what is that? They bounce. The collisions are elastic, right? Collisions are elastic. They follow Newton's laws. They are made of molecules are moving in random directions. The size of the molecule is much smaller than the average separation between the molecules. Molecules exert no forces on each other. Okay. So now we then have this, the probabilistic derivation of the Maxwell-Boltzmann distribution. Maxwell was a famous physicist who did work in many different fields. One of the fields he did was this Maxwell-Boltzmann. Okay. Now, Maxwell-Boltzmann equation developed a probability of the speed of with temperature. Okay, probability of the speed is a very complicated formula. You can look up how Maxwell-Boltzmann is derived. Okay, but the probability of the speed with respect to is defined by this. Okay, now if you do various integrals, right, now you will then end up with each of these values. These all come from the probability, right? So root mean square is what? First you get the mean, right? Integral PV dV. you get the what is that? What is the average? V times P. P is the probability, right? V times P, right? So that will give you the sigma pi vi, right? It will give you the velocity, the speed, right? Speed is given by the average speed, right? Sigma pi vi will give you the average. Okay. Now, the from the average, you can then calculate the root mean square. Okay. Now, the most probable speed is the speed at which is the peak of this curve. How do you calculate the peak of this curve? You take the derivative, right? So if I give you the Boltzmann distribution, you take the derivative and look for the maxima, you will get this point, right? How do you get the mean speed integral PV times d, right? So so this is a sigma pi vi, right? Will give you the expected value. Now from the expected value, and this is the most probable value based on the maximum of the curve, maximum of the distribution, right? Now root mean square is x minus x bar, the square root of x minus x bar by sigma, right? Sigma is what? V square v square times p of x, right? So so you get the variance, right? So variance is so from that you can calculate the value of the v minus v bar the whole square by will give you the variance, and then square root of the variance will give you the root mean square, right? So that'll give you the standard deviation. Root mean square is what? Um, v minus v bar the whole square, right? So that will give you the uh, root mean square, root square root of the mean, right? So uh, v minus v bar whole square. See, look at how he's done all these integrals, right? So v bar is v f of v dv, right? Therefore, that he calculates v bar, right? The average speed is calculated from that, and then the next one is the deviation from can be taken from the video, right? You can understand how they calculate this, right? So from that you get these three formulas. The RMS is square root of 3 RT by M. The peak is 2 RT by M, square root of 2 RT by M. This is 8 RT by pi M. The mean speed is 8 RT by pi M. He is deriving the mean speed here, 8 RT by pi M. Okay. So those are the three values, and then you can take the derivation from the book. But let us now move on. So you must understand the thermodynamics in terms of some of these derivations which are related to kinetic theory of gases, but they're not that central to what we are looking to learn, right? We already looked at the KTG, right? Kinetic theory of gases. Right now, let's not get caught up in that. We'll do a separate lecture on kinetic theory of gases. Okay. So the first law of thermodynamics, right? Let's go on to the first law of thermodynamics. So the first law of thermodynamics states is actually a conservation of energy law, a macroscopic approach to thermal properties of matter, right? So now systems in the rest of the universe, system is separated by a wall, right? If the quantity of heat supplied to a system is capable of doing work, the quantity of heat absorbed by the system is equal to the sum of the increase in its internal energy and the external work done by it. PdV is the work done, right? Now, whatever is supplied as heat is either going to lead to work being done or absorbed as internal energy by the system. This is essentially a law of conservation of energy. Heat is supplied, work is done, or internal energy is increased, right? You either, when you do some work, right? So either the kinetic energy increases or it does work. Or its internal potential energy increases or the kinetic energy increases, right? So that's the what this is all about, right? So either it does work, which leads to something else getting that energy in the form of like mechanical work, right? You do mechanical work, or its internal energy will increase. So you have a closed system, I supply heat to it, its internal energy will increase or it will do work. The heat supplied will do one of these two things only. Now, what do we mean by internal energy, right? So if you heat a pan, right, of water, right, and in a closed pressure cooker, right, pressure cooker is a can be thought of as a system if you keep the lid closed. Otherwise, if every now and then it lets out steam, that is a control volume, that makes it a control volume, right? But then if you keep it completely locked up, what is going to happen? You supply heat from the bottom, right? The temperature keeps increasing. That's not doing work, right? Now but then let's say on top of, instead of a lid, you had a a mass, this kind of a mass, like we saw in the previous uh, here. This kind of a mass, right? It's a pressure cooker with water, this kind of a mass on top, right? So if you keep heating it, what happens? If you keep heating it, then slowly that water's temperature will go up. So ms delta theta is happening, right? And some of the water is going to become eventually gas, and it is going to then have to push the um, um, the weight up. So pushing the weight up is what? Mg times by a distance k. Let's say it pushes it up by a distance k. Mg times h will give you the work done, right? Inside, what has happened? The internal energy has gone up. Ms delta theta plus ml. Okay? Ml is when it converts from water to gas. So that's how you look at these internal systems. I gave you this example so you understand how thermodynamics internally looks at these things, because it's very important to solve problems also. Please do not think that we are what we are teaching does not help you get marks. It does help you get marks. The system is, you look at the system, look at heat, just like we looked at in calorimetry, heat loss equals heat gain. Now you have heat and work. Okay, and the system and the rest of the universe, they have a heat capacity. So Newton, this first law of thermodynamics, basically heat supplied leads to either internal energy or work done. But remember the convention. We already discussed the convention, right? The system is divided into two equal halves in equilibrium. Extensive properties, thermodynamic variables, as we said, extensive or intensive properties. Extensive is, there's a summation of the values, volume, mass, etc. Intensive are things like pressure, temperature, right? And so these calculations that we do in thermodynamics, they are very commonsensical and intuitive, but at the same time they're not so intuitive if you don't understand what all happens. Okay, so you try to understand how these things are evaluated. Okay? And then once we finish thermodynamics, we will then switch to go back and do the kinetic theory of gases, so you understand that as well. Okay, so now heat exchange is happens through a diathermic wall. Okay, now a porous wall will allow exchange of particles as well. Like for instance, a semi-permeable membrane you may have heard in the case of when water purification. They kind of use various forms of what is called osmosis, etc. Right, now an adiabatic wall, the system is isolated. Only a mechanical interaction is possible. In adiabatic systems, this side and that side are separated by a Lakshman Rekha, as we discussed before, right? Porous means things can go this way and that way. Diathermic means heat can go this way and that way. Okay. Now, adiabatic means also there's no heat transfer. Okay. Adiabatic means there's only, the system is isolated. You can only apply and change the pressure, that you cannot change the temperature. So this is the same as isothermal. Isothermal, right? So thermal equilibrium, right? PV equals nRT. Okay, so notion of equilibrium and quasi-static processes. So we you have to spend enough time understanding these various, uh, isobaric, isochoric, etc., etc. You must understand these PV diagrams. You must understand this other term called entropy eventually. And when you include ST and PV together, then you have this whole system of equilibrium, as we teach thermodynamics. Okay, so these are PV equals nRT, adiabatic process, right? And so these processes are defined in thermodynamics. Okay, so uh, delta Q equals delta U plus delta W. Okay, so remember, the first law of thermodynamics is the same as the conservation energy. What is internal energy? Internal energy represents the is tied typically to the temperature. Okay, so higher the temperature, higher the internal energy. In most cases, ms delta theta, as we explained it, right? Now also, when you convert from latent heat, you supply ml, right? When you convert from liquid to gas, that also increases the internal energy. M times L leads to change in the internal energy. Okay, so but on top of that, it also has the ability to do work, right? So keep that also in mind. So now, and the ability to work is integral P dV. So with that, I'm going to stop today. But understand the basics of this thermodynamics, because next time we are going to introduce this other term called entropy, S. Okay, so Q, W, U. Okay, so understand these things. When you study thermodynamics in the context of chemistry, chemistry has a much more sophisticated understanding, because they are the people who finally burn the coal and burn the oil. They are the people who refine the petroleum. They are the people who typically do justice. Chemistry is the central science in these things. Okay, but you must understand physics also. You must understand thermodynamics from a physicist's point of view, and also from a chemist's point of view. When you do, you will then become a better engineer, and also understand how these systems can be studied. The human body is also a system. A tree is a system. Okay, and you will understand the flow of energy in the universe as it happens. Okay. With that, I'm going to stop because we've run out of time. But please try to reason. Thermodynamics is a reasoning science, and things happen with great beauty. And one must understand thermodynamics very well. All right. So with that, I'm going to stop, and let us continue our discussion next class. And I do class 11 on Saturday and class 12 on Sunday. And there's a lot of material that is taught as class 12 material for students also. So please look to attend that class as well. So with that, I'm going to stop, and we'll continue our discussion next class. All right.